So now in the second part of the video for section 10.1, we're going to focus on hypothesis testing for the difference of two proportions. And we're going to go under the general, in all these problems, the null hypothesis is basically that the proportions are the same. P hat sub 1 minus P hat sub 2 equals 0. And then we'll have an appropriate null hypothesis, maybe that the first proportion is greater than the second, it's less than, or just they're not equal to each other. One-sided, two-sided. Excuse me. In any case, what we had done before is we had, when we were working in chapter 9, we had a z value. Well, it's going to be the same type of concept now. It's going to be the difference in the two proportions minus the hypothesis of the null portion. The hypothesis, the null hypothesis for the difference of the proportion, which is basically, hey, they're the same. The difference is 0. And then we're going to divide by the standard error of P hat sub 1 minus P hat sub 2. It'll look very much like this. And again, I just wrote, hey, instead of standard error, I wrote standard deviation. The question is, what do we use for that standard deviation of P hat sub 1 minus P hat sub 2? And if we recall, from when we worked in chapter 9, when we did this, our null hypothesis was that the proportion was equal to P sub naught, whatever our null hypothesis proportion was that we work with. That's what we used in the go-around. But this time, now that we're working with two samples, how are we going to estimate P? What can we use? It can't be a P0, by the way. We'd almost think, hey, that value is 0. If you think about the difference of two means with our proportion, with them both being equal. In any case, what's the important thing to do, and how can we go about doing this? Well, first things first, with our null hypothesis, we're assuming that these two proportions are equal. And what's that mean? Well, even though they're coming from different places or whatever, they're all, quote, kinda, we're thinking that they're all the same. It's almost like they were just coming from one big population. So sure, we might have two different samples in two proportions, but if we think they're all equal to each other, we could almost treat this just like we're taking one, quote, big or consolidated sample and getting a proportion out of it. So what's that mean? Well, it translates into the concept that we will create what I'll call a combined, and the book does the same thing. They maybe use a slightly different term, but it'll be a combined P hat. We'll call it P hat sub C, which kind of means combined. It's our best guess as to what we think that standard error should be, or what the proportion should be in the first place. So if we think everybody's the same, what will we do? Well, to get that sampling distribution standard error, we're going to go with the assumption that our proportion is nothing more than the number of successes in the first population plus the number of successes in the second population divided by the total members of those two sample sizes. So we'll take the number of successes in sample 1 plus the number of successes in sample 2 and divide it by the total number, the combined sample total. And what's that then mean? Well, our nice little thing that we have up here now will become pretty complicated, but don't be daunted by that. The new standard error that we'll work with is nothing more than this new consolidated P hat. They'll call it, I think in the textbook, they might call it the pooled proportion, P-O-O-L-E-D. We pooled both of these two different samples together into one big one. So P hat sub C, 1 minus P hat sub C over N1. That's for the first batch that we did, plus for the second batch. Again, notice the same parameters going into our numerator. P hat sub C, 1 minus P hat sub C over N1 the first time, over N2 the second time. So be very, very comfortable with where we get this pooled value. And notice that serves as what we used to use in the prior chapter as our P sub 0. That's going to be what we use for our standard error. And so when all's said and done, what does our Z statistic turn into? It turns into P hat sub 1 minus P hat sub 2 minus 0. Remember, that's the null hypothesis at work there, divided by the standard error. Once we got our good old Z value, we run the same type of thing before. We'll go ahead and get our P value, and we'll go ahead and apply that against our alpha level to determine whether we're going to keep the null hypothesis, fail to reject it, or decide to reject the null hypothesis. So that's the nuts and bolts of this. Spend some time in the textbook to make sure that you're very comfortable with what this pooled proportion does. P hat sub C. Understand this piece. It's a key to a lot of what you'll do. So with that in mind, let's go into the examples. And so what we're going to do is we're going to work example 2, 3, and 4. 2 surveys, SRS of 80 students in school 1, with 19 coming back and have not eaten breakfast, and SRS of 150, with 26 who had not eaten breakfast. Do these data give convincing evidence of a difference in the population proportions across those 2 schools? So let's work with our setup here. Got a sub 1, got a sub 2. You can see all the appropriate numbers. I've gone ahead and taken my p-hats out to 4 decimal spots. Sample size 1, 80. Sample size 2, 150. My null hypothesis is that p-hat sub 1 minus, or p1 minus p2, rephrase, p1 minus p2, population proportion for the first minus the population proportion for the second, they're the same, would be equal to 0 if we're doing subtraction. My null hypothesis is that the population proportions for the 2 schools are different. What's my pooled parameter, my p-hat sub c? Well, 19, 26, 19 plus 26 over 80 plus 150, 45 over 230. My pooled parameter is 0.1957. I'm going to test at an alpha equal 0.5 level. Problem didn't state it, so that's what I'll go ahead and set as my alpha level as I work through this hypothesis test. Now, a couple other key things. The problem said, I'm not going to go back and pull it, that there were at least 1,500 students in both schools. 80 and 150 therefore meet the 10% condition. I have a simple random sample in both cases, 2 SRSs. I'm good there. And by the way, my large counts, 19 and 61, 26, 124, all bigger than 150. That allows me to do the work and go ahead and run a z-test. And so here we go. I'm going to calculate my z-value. Well, it's 0.2375, p-hat sub 1 minus p-hat sub 2, the 0.1733, minus 0. And then kind of a little bit small here, but notice what have I used? P-hat sub c, 1 minus p-hat sub c, multiply them together, and build 2 different fractions. Over 80, that's my n sub 1, plus 150, that's my n sub 2. And when I get this all done, that numerator will become 0.0549. My denominator is nothing more than 0.2375 minus 0.1733, 0.0642. When I crunch the numbers to that, I get a z-value of 1.17. Now, this is a 2-sided test. And so, what do I want to look for? Well, I'm going to have to double my little normal CDF calculation I'm going to do. So 2 times normal CDF, and I'm going to go ahead and just capture the part of the curve that is greater than 1.17. So I run normal CDF, 1.17, 5 nines. I'll get 2 times 0.121. So this is 12.1% that lives over there. 12.1% lives over there. Add them together and I get 24.2, 0.242 as my p-value. Since my p-value is much greater than my alpha level, I'm going to fail to reject the null hypothesis here. There's not convincing evidence that the true proportions are different for these 2 populations. So that's working through one of these problems in a nutshell. There's a lot of work here, I freely admit that for sure. A lot of different stuff that you had to walk your way through here in the calculations. But what are you trying to do? Bottom line, you're just trying to get yourself a z-value. And once you got a z-value, you're off to the races. All right. Our next example, example 3, worked on a volunteer test. And there's an interesting thing that'll come up here. We'll talk about some of our conditions in just a little bit. But note, this is an experiment. We're doing inference on an experiment here, as opposed to inference on a survey. There's a couple of interesting ramifications. The textbook will probably do a little bit better job giving you detail than what I'm going to do in this very short video. But just make sure that you realize example number 3, we're trying to do inference off of an experiment as opposed to inference off just a pure sample. So in any case, here's our series of pieces of information. We got our group 1 that took the drug, group 2 that took the placebo. 56 out of 2051, there's my first proportion, 0.027. My second proportion is 0.041. Sample sizes 2051, 2051, 2030, respectively. I'm going to again test the probability that the proportions are equal in the two groups, the drug group and the placebo group, versus P1 minus P2 is less than 0, which would imply that what? Fewer heart attacks over here. We'd like to see that as a negative number. It would give us some type of evidence, hopefully, that what? That this drug was effective. So there's our basic setup. Do we meet a couple conditions here? Are we doing random experiments? Are the groups randomly selected into the two pools? The answer is yes. By the way, we're taking what? We're running an experiment on everybody in, quote, our two populations, in our patient populations. We don't really need to worry. There's no random sampling of these people at this stage. They're all in it. They're all getting that experimental treatment, whether it's the drug or the placebo. In this particular instance, we do not need to worry about the 10% condition. Read that part of the textbook. It's a very interesting set of paragraphs or whatever. Be comfortable with. This is one place where the 10% condition doesn't impact us. We're taking everybody. We're not doing sampling without replacement on this go around. All right. Do we meet the large counts condition? Well, we still need to be concerned about that. Yeah, 56, 2051 minus 56, both those numbers bigger than 10. 84, 2030 minus 84, certainly bigger than 10. We're good and golden on that. So there's our hypothesis. We'll test again at what level? Well, in this case, I think the problem asked us to do what test level? They asked us to work at an alpha equals 0.1. So I'll go ahead and just put that up there. We didn't have to select it this time. What's my p hat sub c? 56 plus 84 over 2051 plus 2030. It gives me a value of 0.034. My z value now becomes what? Well, P1, p hat sub 1, minus p hat sub 2, 0.027 minus 0.041, minus 0, because we're assuming that in the hypothesis, P1 minus P2 is nothing more than 0. And there comes our good old standard error, by the way. 0.034, 1 minus 0.034, that would be the 0.966. See my numerators repeat. Notice I divide the first time by 2051, second time by 2030, and what will I walk up into? Well, I'll have negative 0.014 over 0.00567. I've taken these out to a couple levels here. My z value is negative 2.47. So, what kind of test am I doing? I'm doing a one side. I'm looking for the probability that I'm to the left of negative 2.47. And when I run that, I'll run normal CDF, negative 99999. I'll work way over here on the curve, all the way up to what? Negative 2.47. And I'm going to come back with an answer that is 0.006, less than 1%. Since my result is less than 1%, my alpha level, I have sufficient evidence to reject the null hypothesis. I think there's convincing evidence to show that the drug is effective in reducing these medical issues. So there's that problem. A lot of detail on this one, a lot of work through it. Hopefully you're starting to feel a little bit comfortable with this. Our final example, example 4, focus on just a comparison of President Obama's approval rating from the year 2012 through 2013. I wanted to look and see what was the change in his approval rating over that period of time. It was done through two simple random samples of 1,500 individuals in the months of October of 2012 and 2013. In 2012, there was a 52% approval rating, a 46% approval rating in, in 2013. And what you were asked to do is just build a 90% confidence interval for that change in approval rating. It's a multiple choice question. We'll go ahead and just work through the numbers though with our example here. So I've kind of written our nomenclature just a little bit different this time. Instead of using 1 and 2, I decided to do subscripts of 13 and 12. So here's our 2013 results, the 46% approval rating out of a sample of 1,500, 52% approval rating the year before in 2012 out of a sample of 1,500. And we want to check basically the change from 2012 to 2013, and we'll do that as p hat 13 minus p hat 12. Now, our conditions met. SRS has existed in both years. 1,500 is certainly less than 1/10 of the entire population, so we're good there in terms of how our sampling worked or whatever. And we have the large counts condition met for sure. 40%, 46% of 1,500, 54% of 1,500, 52%, 48% of 1,500. All four of those numbers are greater than 10. And that certainly allows us to go ahead and do a confidence interval. All conditions have been met. So we're going to start. We need to build kind of what's our distribution. Well, the distribution of the difference of the two proportions is p hat 13 minus p hat 12. That's negative 0.06. The approval rating did, at least in terms of the sample numbers, had gone down. What's our standard error? Well, 0.46 times 0.54 divided by 1,500 plus 0.52 times 1 minus 0.52, 0.48. Again, divided by 1,500. And again, we'll go as we work these numbers through. That sample error will be about 1.8%, 0.0182. We need a 90% confidence interval. So here's my nice little shaded diagram of 90. What do I know? 5% this way, 5% over here. That location is the 95th percentile, inverse normal, 0.95, gives me 1.96. That becomes my z value. And so our interval is nothing more than negative 0.06 plus or minus our z value, 1.96, times our standard error, 0.0182. And the values that come back are negative 0.095 and negative 0.0243. And if we look at all the answers that the problem gave us, again, I went to a slightly deeper level of precision, but the best and closest answer would be option B. So hope this helps you a little bit. By the way, if we look at this at a 90% confidence level, what do you notice? 0 isn't in this interval. They're all negative numbers. That does give us kind of an idea, at least at the 90% confidence level, that maybe we can feel comfortable that there is a decline in the approval rating that is statistically significant, or at least so at the 90% confidence level. So this wraps up all I wanted to cover with this section. For the time being, there'll be more. We'll let you look at the calculator pieces that you can use to handle these problems as well. But for the time being, we'll just kind of focus on the long-winded, kind of doing the hand calculations as we've done before.